Reaction coordinate diagrams, or energy diagrams, are not really covered in our book, but they are important. They help to explain a lot of phenomena that we look at in chemistry, in general chemistry in particular. So without further ado, what are we going to learn from this particular presentation? So we will look at reaction coordinate diagrams to graph energy changes in chemical reactions. We will define exothermic and endothermic reactions using energy diagrams. And we will use reaction coordinate diagrams to talk about activation energy, enthalpy of reaction, and catalysts. Reaction coordinate diagrams, or energy diagrams, are often used to illustrate a simplified version of a reaction. The axes are potential energy versus reaction progress. Now this is important. Reaction progress does not refer to time, but simply that the reaction is taking place. On the far left of each one of these diagrams, the horizontal line represents reactants. On the far right, the flat line represents products. The reaction proceeds from left to right. Some reactions are exothermic and some are endothermic. Endothermic reactions absorb energy to occur, so the energy of the products is greater than the energy of the reactants. An endothermic reaction vessel will absorb heat from the surroundings, which makes it feel cold. Reactions where the products have a low energy than the reactants are called exothermic reactions. These reactions give off heat and feel hot to the touch. So negative sign is hot, positive sign is cold when you're looking at these diagrams. Also, an additional caveat here, anytime you give off energy, it's going to be negative. Anytime you absorb energy, it will be positive. Let's define some other terms that are also relevant. The difference in energy between reactants and products indicates the heat of reaction, delta H XRN. The heat of reaction is represented on this graph by a solid black vertical line on the far right. No matter the way you get from reactants to products, delta H RXN is a fixed value. Full disclosure, it's fixed for a given temperature. It does change for other temperatures. I digress. So Hess's law, which you'll get more information about on another presentation, shows that it does not matter how you do the reaction, it will always have the same energy of reactants and products. And the difference between the two is constant as a result. This is called a state function. State functions are reversible, they're consistent/constant, and integrable and differentiable, which is a very math-oriented comment. I am, however, a math-oriented chemist. Reactions are started by collisions. Collisions can result in higher energy states for the molecule. So the hump in between reactants and products represents the activated complex. The activated complex is the highest energy state that degrades into products. Usually, it's pretty short-lived, and it's composed of the reactants falling apart into products. So if you have a complex made out of two different reactants, that short-lived complex decomposes into products. But you can also have a high-energy version of a single compound that degrades into products. Either way, the difference in energy between the activated complex and the reactants, given by the green vertical line on the left of the black vertical line, is referred to as activation energy, given by E sub A. This energy must be overcome so that a reaction can take place. The absolute highest energy on the diagram is called the transition state. There are, FYI, more complicated diagrams than what we're currently looking at. So here's one such diagram. Sometimes reactions take place in more than one step, and in those cases, flat lines, or minima between the reactants and products are called intermediates. There are two intermediates in this particular diagram. 1, 2. The reactants and products do not change, nor does the heat of the reaction. Those things are constant via Hess's law. There's also a separate activation energy for each step. For the first one, we have 3 activated complexes represented, 1, 2, 3. And then we have intermediates, 1, 2. For the first hump, the activation energy is the difference between reactants and activated complex 1. For the second hump, it's between complex 2 and our first intermediate. For the third one, it's between complex 3 and the second intermediate. Either way, activation energy is a fixed quantity. All right, so this brings us to our final concept we can learn from our wonderful energy diagrams. So you'll note in this diagram, we now have 2 different humps, and both of them have the same reactant and products. The lower hump is the catalyst. Most often, when you use a catalyst, the reaction speeds up because it provides an alternative, lower activation energy pathway for the reaction to occur. Now, keeping that in mind, most often a catalyst has not moved around in the solution, but it orients the reactants so that the reaction is more likely to occur. So, in other words, it lines up the reactant or reactants to form an activated complex based on the orientation. This reduction in the cost of activation energy results in a large increase in rate. You'll note that the activated complexes are different energies, and in fact are completely different transition states between the catalyzed reaction and the normal reaction. When you use a catalyst, you are providing a different pathway for the reaction to take. An analogy which helps me with this concept: when you drive over a mountain, it takes a lot of energy and a long time. But when you drive through a tunnel in that same mountain, it takes both less energy and less time. So if you change your pathway, you can reduce the energy of reaction and thereby increase the rate. So you're reducing activation energy, increasing the rate. Catalysts are not used up in the reaction, so the heat of reaction is constant even with the catalyst. That is still true. So you may have added something, but you've added it on both ends, which means that your activation energy, different, but your heat of reaction, constant. This has been really well studied, and it matches with Hess's law, which we already mentioned before. We're representing 2 separate pathways to the product, but the same difference between the reactants and the products. It's the same no matter what you do to complete the equation. The reaction has sped up, but the heat of reaction remains the same. Yes, I know I already said that, but it's important, so I said it again. To summarize, reaction coordinate diagrams or energy diagrams can be used to symbolically represent a course of a reaction. Reactants are often on the left, products are on the right. Activated complex or complexes are the hump or humps on the diagram between reactants and products. Activation energy is the activated complex subtracting the reactants. The heat of reaction, delta H XRN, stays constant no matter the pathway used. So that is Hess's law. Hopefully, all of that made sense. I know I got a little bit garbled for some of it, but I'm hoping it got across. I will see you Wednesday.